We will start the third part of this course. During this part, you will learn to use operational amplifiers. You will learn the methods to analyze them and how they can be used to achieve a variety of tasks. In this first lesson, you will learn one of the most useful concepts in engineering, feedback. Feedback is fundamental when designing circuits using operational amplifiers. For that reason, we will dedicate a full lesson to understand it. This lesson is sketched out to be a hypothetical situation where you have to design an amplifier. You will face issues when trying to solve a task, but with my help, we will find the solutions. The objective of this exercise is learning why feedback is so awesome. Here are the specifications that your supervisors gave you. You need to find a solution to amplify a signal in the range of 0 to 1 volt to be in the range of 0 to 20 volts. That means that you need an amplifier with a gain of 20x. We can see in the diagram below how the circuit will be. You have some source providing a voltage that can be a measurement from a sensor, and you have to amplify it with your solution 20 times and provide an output signal. The first natural thing to do is to look in catalogs from different manufacturers in order to find if there is a solution that fits your needs. And it turns out that you're lucky and you find a manufacturer that sells amplifiers with a gain of 20x. You can simply buy it and solve the issue. But there is one issue. This specific manufacturer only sells boxes of 10 amplifiers. You will need to buy 10 even if you only need one. Additionally, the amplifiers are a bit expensive. Anyway, you decide to buy them, and after receiving them and test one of them, you find that it works as expected. Here are the results. For a sine wave of 1 volt, you get a 20 volt output signal. You decide to present the solution to your supervisors, but when you show them the amplifier, they'll tell you that the specifications have changed. Now you need an amplifier of 10x instead of 20x. And that's unfortunate. Now you have a box of 20x amplifiers that you have to throw away and get new ones. But your supervisor tells you that there may be a solution to reuse the same amplifiers. Then you remember that in one of our previous lessons, you learned the voltage divider circuit. That circuit can help you reduce the input signal to the half. So a gain of 0.5x followed by 20x makes a total amplification of 10x. The new system looks like this. You have a pre-amplification stage of 0.5 with a voltage divider, followed by the 20x amplifier. It's time to show this solution to your supervisors. When you show the solution, your supervisors are not very keen on the idea of adding a voltage divider at the input. The main reason is that they do not have enough information about the characteristics of the connected sensor. That makes picking the values for the resistor divider more uncertain. As we learned, the values are important and can affect the performance of the circuit. For that reason, you have to find a new solution. But at this point, everything points out to the idea of buying new amplifiers. After reading again the documentation, you find that there is something that you have overlooked. There is a second input in the amplifier labeled minus. In your test, you have only used the input labeled plus and the minus is connected to ground. The amplifier behaves as following. It takes a positive voltage labeled plus or P, subtracts the negative voltage labeled minus or N, and multiplies the result by 20. It will be interesting to see if we could use this other input to reduce the gain of the amplifier. Let's rearrange the formula so we can obtain what should be the voltage at the negative input in case we want the amplifier to behave as it will be 10x. To calculate it, we need to provide the input voltage P, the desired output voltage, and that will give us as result the voltage N. Let's create a table with the results. In the first case, we have that for an input voltage of 0.1, the output voltage must be 1 volt, and the necessary voltage at the negative pin must be 0.05. We can continue calculating them until we reach 1 volt. In such case, the output voltage must be 10 volts, and the negative voltage needs to be 0.5 volts. As you can see, there is a pattern. The negative voltage is in all cases half the input voltage. In principle, we should be able of using a voltage divider at the input in order to obtain the voltage at the negative pin and achieve an amplification of 10x. But we already decided that adding a voltage divider at the input is not acceptable on this design. Where else can we get the voltage from? Maybe we can add a voltage divider at the output. If we multiply the output by 0.05, we can obtain the desired negative voltage. Let's test the idea and make a few simulations. The system looks like the following diagram. We have the output of the 20x amplifier connected to a gain stage that allows to take part of the output and feed it back to the amplifier. We can experiment with different values of feedback. When the feedback is 0, we can see that the amplifier behaves just as before. The output is 20 times larger than the input. But as we start increasing the feedback, we can see that the gain is being reduced. We can even achieve a gain of 1. If we put the gain to 0.05, we can see that we have the desired gain of 10x. Let's try to obtain a generic formula to calculate the feedback. We will start with the amplifier formula. In this case, the uppercase G represents the gain of the amplifier. The voltage at the negative pin is given by the output times the amount of feedback. Replacing that value into the initial formula and solving for the output voltage, we obtain the output voltage as function of the feedback, the input voltage, and the gain of the amplifier. The effective gain of the amplifier, represented by the lowercase g, can be defined as follows: g uppercase divided by 1 plus f times g. If we solve that equation for the feedback, we get the formula for the necessary feedback in terms of the amplifier gain, which is uppercase, and the desired effective gain, which is lowercase. We can corroborate it by putting the numeric values of the example, and we can see that we obtain the same value that we determined experimentally. And that's it. After you present this solution to your supervisors, they are very happy with your solution to the problem. Now we need to build more of these circuits so you can test them in a real scenario. After building more amplifiers, you start noticing that not all of them behave the same. For some strange reason, some of the amplifiers do not have an exact gain of 20x. Some go as low as 18x, and others can go as high as 22x. When testing all of them, you find that the amplifiers have a variability of 10%. The output voltage could be either up 2 volts or 2 volts below the desired value. After accumulating the results, we can obtain a plot like the following, which shows the results according to the probability. However, when comparing this plot against the measurements on the amplifiers with feedback, which have a gain of 10x, we can see that they behave more accurately. The width of this band is more narrow compared to the 20x amplifiers. Let's try to calculate the variability for both cases in order to draw some conclusions. Let's start by calculating the actual gain of an amplifier without feedback. In this case, the actual gain, which is the lowercase g, is equal to the amplifier gain, which we have been representing with uppercase G. We can replace the amplifier gain by the gain G0, which is the design gain, plus minus a variability value represented by V. For the previous example, the 20x gain amplifier has a variability of up to 10%, we can calculate what should be the maximum and minimum for the gain in the following way. We can add and subtract to 20x a value corresponding to the 10%, which in this case is 2. This results in a minimum and maximum of 18 and 22x gain. For the amplifier with feedback, we replace G uppercase by G0 plus V. If we put the numeric values we have, we can calculate the minimum and maximum gain that we will obtain. If you pay close attention to these numbers, you can see that in the amplifier with feedback, a variability of 10% is being reduced to less than 5%. This is a very interesting effect. Let's see what happens with the variability when the gain of the amplifier changes. This plot reveals something very interesting. What you are seeing is the minimum and maximum gain that an amplifier with feedback will have for different values of amplifier gain. For example, if the amplifier has a gain of 20 plus minus 10%, once we add the feedback to achieve a gain of 10x, the minimum and maximum will be 9.47 and 10.47, which are the values that we calculated before. If the amplifier had a gain of 200 plus minus 10%, the variability is less than 1%. If we keep increasing the gain of the amplifier, the variability becomes less and less important. Let's see what happens with even higher values of gain. This is the same plot, but now the amplifier gain values are very large, from 100,000x to 400,000. We can see that with this gain, the minimum and maximum values are very close to 10x. The variability is negligible. If we take the formula for the amplifier with feedback, including the variability term, and we calculate the limit when the amplifier gain is infinity, we obtain an interesting result. If the amplifier gain is very large, we can assume that the actual gain is defined by the reciprocal of the feedback. The variability doesn't even show. It is negligible. Once you have discovered that all the 20x amplifiers have variability problems, in a Deus Ex Machina resolution, you suddenly find that there is a switch that you can flip, and that will turn the 20x gain amplifiers to 200,000x. As we learned, with such a high gain, the variability is not important. You can use feedback to make the amplifiers 10x gain. When you present this solution to your supervisors, they are very happy with the result. To summarize this lesson, we learned the importance of feedback in amplifiers. It can be used to control the gain of an existing amplifier. Since amplifiers have a variability due to the imperfections in the manufacturing process, we can use feedback to mitigate this issue, especially in amplifiers that have very high gain. In the next lesson, we will start analyzing electronic circuits using operational amplifiers.